In this video, we're going to talk about the kinematic equations, which are pretty much equations that don't care about the reason for the motion. It's just looking at the motion without forces, for example. And then we'll get into Newton's laws and forces. And lastly, we will cover this momentum concept and impulse, and we'll get into what a momentum update and a position update is all about. And we'll try to apply these to two problems. One is a ball kind of being thrown against a wall at an angle, and the other one has to do with a ball being kicked. When you're looking at one-dimensional motion, for example, the position of an object that's moving can be tracked with a position time graph. And so you know its position on an x-axis, for example, at any point in time for the motion. And so when you have a graph like this, you'll know that you can take the derivative or look at the slope of this position time graph in order to get to velocity information. And so, for example, right here at the top of the position, the slope is 0, which if you translate that down to the velocity, it shows that the velocity at that time is 0. And you can take the derivative again, in other words, looking at the slope, and we can see, for example, right here the slope is 0, and translating that down to acceleration, which is change in velocity, we're seeing that that translates down here to 0 for acceleration. And so as you go down, you are taking the derivative, you're looking at the slope, the rate of change. And then as you go up, you're taking the integral, you're pretty much looking at the area under the curve. And so that is some basic ideas regarding kinematic equations and keeping track of position. But let's get into the actual equations and where they come from. Equations of motion are very useful because we can track the final position as a function of time. And so sometimes these equations of motion can be pretty complicated, but we're going to simplify it down, making some assumptions. And so really the 5 variables that we need to consider is the displacement, which is change in position. So this includes the final and the initial position. And a lot of times our initial position is 0, but not always. It includes the time we care about, and that a lot of times your initial time is 0 when you start the stopwatch, but not always. We care about how fast we're going initially. What is your initial rate of change of position? And so we also care about how fast you're going at the end of that time interval, so your final velocity. And then if there was some change in your initial and final, we care about the acceleration. So what is the rate at which that velocity is changing? And so when we know all 5 of these variables, we really know a lot about the motion at hand. And so some general notes here, we know that this triangle symbol delta it means change, final minus initial. And so when we have some displacement, it's the final position minus the initial position. We know that negatives and positives can be used for direction in one dimension. So for example, to the left is negative, to the right is positive. We also know that we can write it, if it's in the x direction, we could use delta x instead of delta r. So delta r is a little bit more generic. If it's in the y, we could use delta y. And that's just, again, final minus initial for displacement. And a lot of times we can write t instead of delta t because we're assuming that ti is 0 a lot of times. And then most importantly, we're going to make the assumption that our acceleration is constant. In other words, there is no change in acceleration. The change in acceleration is 0. I'm accelerating at a constant rate. And so when we make that assumption, some awesome things happen. And so we end up with this equation that we'll see in a second. But as an example, what we can do is say that I'm at a stop sign and I'm at an initial position of 0. And I'm also at rest, so I'm not moving. But now I put my foot on the gas and I'm accelerating at a rate of 2 meters per second every second for 5 seconds. And so it would make sense then, 2 times 5 is 10. I'm going to be going 10 meters per second after that 5 seconds. And you can also find out that you're going 25 meters in terms of your displacement. And that would kind of fully describe that situation as an example. And what we want to be able to do is kind of calculate this if we're given a problem. If we're missing one of these 5 variables, we can start to be able to calculate what it is and make predictions. And so our equation of motion with this calculus coming in, assuming that you have this uniform or constant acceleration, we can start with this equation of motion here your final position equals your initial position plus your initial velocity times time plus 1/2 times the acceleration times time squared. And so we use the derivative, like we said on the last slide, to get to velocity. And so we're taking the derivative with respect to time. We're going to use the power rule. We multiply the n down front, and we subtract 1 from the power. And so the Ri disappears because there's no t. We're just taking the derivative of a constant, which is 0. We take the derivative of this here with respect to time. The t goes away. We take the derivative of this here. The 2 comes down, gets rid of the 1/2, and we still have a t left over. And so we end up with the final velocity equals the initial velocity plus the acceleration times time. We take the derivative again, and you're going to see something really interesting. And so we get rid of this because there's no time. So derivative of something that doesn't have time in it with respect to time is going to be 0. And then we have the time here goes away. So we're basically saying here that your final acceleration must equal your acceleration, and it doesn't depend on time. So it's not a function of time, meaning that it's not changing with time, so it is constant. And so what that means is that this equation is really only valid when you have a constant acceleration. It's a really important assumption we're making. And so we move on to generating these 5 kinematic equations, which are really useful tools in physics. And so these equations do not really care about the cause of the motion, because that's what kinematics is all about. We don't really care about forces or what's causing the motion. We just want to describe the motion mathematically without references to its causes. And so the first one, your average velocity is displacement over time. We can rearrange that formula. We can also write your average velocity as pretty much your initial velocity plus your final velocity divided by 2. That's going to be your first one. Your second one here is just the definition of acceleration pretty much. So you have a change in velocity over time. If that happens, then you have acceleration. And you can rearrange that to be the equation that we had over here pretty much. And then now we're going to take this equation and do some stuff with it. So basically you'll notice that each one of these equations is missing one variable. And we want to generate equations that have 4 variables in them, and they are missing the one that you don't care about. And so what we can do is take the integral of this, and we end up with our function that we had over here. And so we're pretty much, we have 3. These ones are very common. And then some other useful ones, we can take this equation and we can plug it into the other equation that we just generated, and we can make some simplifications. And so we can basically get rid of the variable time, and we can have an equation that pops out here that does not depend on time. So if your problem, you don't care about time, you're not asked to calculate it, and it doesn't give it to you, then you can use this equation. It's awesome. Another thing we can do, we'll start with this equation over here again, and we can, in this case, solve for VI. We're going to get rid of VI through substitution. So we'll kind of sub that in and get rid of it. And so now we have an equation here that does not depend on your initial velocity if you don't know it and you don't care about it. And so we have these 5 equations here summarized, which you can look up, and they're very useful. We can solve a lot of different problems with these. And the way that you pick your equation is you look at the variable that's missing. So if you don't know acceleration and you're not asked to solve for it, then use this equation. If you don't know your displacement and you're not asked to solve for it, then use this equation, and so on. And so that's kind of how you pick your tools. And so this right here is a wonderful toolbox of formulas that can describe motion using this assumption of constant acceleration. But we do want to be able to describe why this motion is occurring, and for that we need to go into forces. So Albert Einstein said that nothing happens until something moves. And in order to change the motion of an object, we need this idea of a force. And so a force is any interaction that, when unopposed, will change the motion of an object. And there's 4 fundamental forces in nature that you can look at. And so we have the strong nuclear force, which is the force that holds together the nucleus of an atom. So you have protons and neutrons. The protons are all positive, and they would love to just repel each other, but the strong nuclear force holds them together. And then we have, that's the strongest force. And then we have the electromagnetic force, which is the attraction or repulsion of charged particles. So, for example, an electron and the positive nucleus, so negative and positive attract. Then we have a weak nuclear force, which is involved in nuclear processes like a nuclear decay. And then we finally have the gravitational force, which you're probably most familiar with, and that's the force between two masses, or at least it behaves like a force. And so we have the new idea of gravity, which is Einstein's theory of space-time, and the bending of that space leads to this idea of gravity, but it behaves like a force, and so we can treat it like one. Now the other thing we can do is look at Newton's 3 laws of motion and understand that an object that's at rest will stay at rest unless it's acted upon by some net force, and an object in motion will stay in motion unless acted upon by a net force. The way to say that mathematically is if there's no net force, F net equals 0, then there's no change in the motion. If the F net is not equal to 0, then there's some change in your motion. Now the second law is really kind of putting a formula to the idea of this net force, and it's a formula based on the mass of the object and the acceleration, and so that's also analogous to your weight. So your mass times your gravitational acceleration, and we could even look at the more generalized formula for gravity, which is your two masses divided by their separation squared times this big gravitational constant. Now the third law is an action-reaction pair, and so it's basically saying that for every action there's an equal and opposite reaction. So imagine you have these two people here, one pushes on the other, but they're going to actually experience the same force in opposite directions, and so the action force is equal to the negative of the reaction force. Now another thing to think about is friction. That's another type of force here. Now friction is opposing changes in motion. It's just opposing motion. And so we have a drag force, for example, that is dependent on the density of the fluid that you're moving through times the area and the coefficient, the drag coefficient, and your velocity squared. So the faster you're moving, the more drag force you're experiencing. You can also represent a resistive force as negative b just being a constant times velocity, so it's a function of how fast you're traveling. The faster you go, the more resistance you're experiencing. Now, another two would be your static friction and your kinetic friction. Static friction being when you're not in motion, and so if you start pushing on something, your static friction is going to equal your applied force until you hit the breaking point, and then it'll be equal to this coefficient of static friction times the normal force. And then your kinetic friction, once it breaks loose, will be the coefficient of kinetic friction, which is less, times the normal force, and that coefficient is dependent on the materials in contact. Now the other thing to think about is electric and magnetic forces. So electric forces are between charged particles, so for example opposites attract and like charges repel. Now we can describe this electric force in terms of Coulomb's law, which is basically very similar to the idea of gravity, where the two masses multiply divided by the separation squared. The two charges are going to multiply divided by the separation squared. We have this Coulomb's constant here. And we can also look at it in terms of an electric field. So if you have a charge and an electric field, then you have that charge multiplied by the electric field to figure out how much force is going to be on that charge. We also have the idea of a magnetic field. So if you have a charged particle moving at a velocity in a magnetic field, it's going to experience a magnetic force. We can also look at the spring force, which is pretty much Hooke's law. And we have this initial length of the spring, L0, and we stretch it to this new length, L. And we know that the elongation then of that spring is going to be L minus L0. And so we can call that S. And so S pretty much represents the elongation of the spring. And we know that the bigger the elongation, the bigger the force. And it's a restoring force, so it's pretty much trying to get back to where it was. And so that's why we have a negative here. And because the force is pretty much in the opposite direction of where it is stressed. And we have the spring constant Ks here, which represents the strength of the spring. So not all springs are the same strength. Now we also have the idea of buoyancy, which depends on the density of the fluid, and it depends on the volume that's displaced by the object, and it depends on the gravitational acceleration. We also have centripetal acceleration, and so if you're traveling in a circle with some sort of angular velocity, we don't necessarily need to change the magnitude of our velocity, but we are changing the direction. And so because you're changing the velocity, even though you're not changing the magnitude, you can still change that direction. We're going to have this new type of acceleration called centripetal acceleration, and that could be considered a new force here. And it's always pointed towards the center of the circle. All right, so those are some of the common forces that you're going to experience. And remember, force is any interaction that, when unopposed, will change the motion of an object. So now we're getting into describing why the motion is changing. And we can also draw free body diagrams, and we can look at what forces are acting on an object and what is going to happen to that object because of it. So a little bit different than the kinematic equations, which don't really care about the cause of the motion. So the last thing we have to talk about before our practice problems is momentum and impulse. And so we have this idea of momentum, which is symbolized by P, because we already took M for mass. And so we have momentum is mass times velocity. So it's pretty much just velocity weighted by mass. And so as we increase our mass, we're increasing our momentum. And as we increase our velocity, we're increasing our momentum. And the units for this is kilograms for mass multiplied by meters per second for velocity. And we also know that it is a vector. And so with any vector, we can break it up into its components. So we have an x component, a cosine theta, a y component, a sine theta. We can find the angle with arctan of y over x. We can also look at the Pythagorean theorem to find the magnitude of this vector. So ax squared plus ay squared, square root of the whole thing. We also can look at the unit vector for any vector by taking the vector and dividing it by its magnitude. And so all those concepts come back into play with this idea of momentum, which is a vector. Another vector is impulse, which is change in momentum. And so anytime that you have a change in your momentum, we could write it as J, but a lot of times we just write it as delta P, which is final and minus initial momentum. And it pretty much has the same units, or a lot of times we do Newton seconds also. And the idea is we are changing our momentum. So how did that happen? Well, we probably had a net force which caused an acceleration, and that acceleration means that there was a change in velocity. If you're changing your velocity, we know that you are changing your momentum, and if you have a change in momentum, you have an impulse. And so over here, we note that if we have a force time graph, we can basically look at this force as a function of time. And if we take the integral, the area under that curve is going to be the impulse. So that's one way of looking at it graphically. The assumption that we are going to take, though, is that our net force, which means our acceleration as well, is constant. And we're looking at small time intervals. And so we're going to deal with this idea of using updates. So it's an iterative process, and you have time steps. And the time steps a lot of times are small. And so we're just looking at what's happening after 1 second, and then the next one, and another second goes by. So what's happening at 2 seconds, another second goes by, what's happening at 3 seconds, and so on. And so what we can do is we can update our position. And so the way that we can do that is look at our position a short time into the future. And what that does, it depends on whatever your position is now and whatever your velocity is now. And so we basically start with this average velocity formula as displacement over time. We recognize that if we had an infinitesimally small difference, we could use the dr dt. And we're not necessarily doing that, though. We're going to break this into final minus initial. And then we multiply over the delta t, and we rearrange, and we get this equation here, which is nice for our position update. Your final position is your initial position plus your average velocity times your time. That's an equation you're going to want to remember. Another one is going to be kind of starting with your delta r as RF minus RI, we can rewrite that as your final position is going to be whatever your initial position was plus the change. And notice how we get back to the equation that we had before after we sub in for delta R. Another cool way to write this, though, is that we plug in for our average velocity as VI plus VF over 2. And then we can multiply top and bottom by mass, and then we kind of turn that into momentum. And so another equation to remember here is this one, because we have our final position as a function of our momentum. All right, and so we look at our momentum update, and so it's the same idea. We have the momentum of your system a short time into the future is going to depend on whatever your momentum is now and the net force that's exerted on it by the system's surroundings. And so we have some sort of an acceleration, so we have a change in velocity over time. Notice that we can also write it as infinitesimally small differences if we were to get into calculus. Now we look at Newton's second law, and so we all know hopefully that F net equals ma, and we can write acceleration as change in velocity over change in time. And we write that as Vf minus Vi. We multiply the mass to both terms, and we get this here, which now we change it into momentum. And because we did that, we have some sort of a change in momentum. This is awesome because it actually links your net force to your change in momentum. All right, and so we have this concept here. We can kind of rearrange it and call it this momentum principle. And so a lot of times in science and also philosophy, we like to boil things down to first principles. And so this is a huge principle in physics that connects the force and your momentum, your impulse, together. All right, and so we also recognize that this impulse, the change of momentum, is actually equal to the integral from your initial time to your final time of your force dt. So up here, like if you had a changing force, if it was not a constant force, you would actually have to take the integral. But this momentum principle is still really cool, and we can kind of avoid calculus like you'll see in some later problems. The other thing that we can do is rearrange it, and we get something that looks like what we had over here for the position update. And so we have this nice formula for our momentum update as well, where your final momentum equals your initial momentum plus whatever net force you have times your change in time. And so another way of thinking about it is that you have your change in momentum, which is final minus initial. We know that your final is going to be your initial plus whatever change there is. And we write that change, as we learned, as F naught times change in time, which is basically what we have here. And then we can divide everything by mass, which is another way of looking at it, because that'll get us to an equation with velocity. And so a lot of times we like to use this equation too. Your final velocity equals your initial velocity plus F naught times delta t over m. Now, one way of looking at this is just saying that this here on the top is your change in momentum, so your impulse divided by your mass. And so we could write it like that if we want. And then the other way we could write it is looking at F net over m as being acceleration. And so you'll recognize this equation from before. It's one of our kinematic equations. All right. And lastly, we can kind of get back to linking it to our velocity. So your final velocity equals your initial velocity plus your change. And so it's all kind of linked together. So this all has to do with changing your momentum, your momentum update, and this has to do with a changing position, a position update. So big concepts here to remember. So let's apply these concepts to two different problems. This one says a ball of mass m is thrown at an angle theta I, and it's going to be respect to this horizontal, this dotted line, and it is going to bounce off the wall with the same speed and the same angle that it hit. And it's asking for what is the change in momentum or the impulse. And the hint here is that you do not know the vector components of momentum, and so to solve this problem you will need to consider the magnitude of momentum and angle to apply trigonometry functions. Now, one thing we want to do is identify the system and the surroundings, and it usually makes sense when you're defining your system to think about what are you interested in. And so we're really interested in the motion of the the ball and what's affecting the ball, what's interacting with the ball. And so it makes sense to put the ball as our system. And the main thing that's interacting with our system in this case is the wall. And so the system could be defined as the ball, and the surroundings can be defined as the wall. And so the other thing to think about is, how are we going to solve this problem? What's our strategy? And so before we answer this, let's look at our picture here and kind of break it down. So we have some initial momentum in the x, and we have some initial momentum in the y here with our first thing here broken into components with our initial momentum. And once we hit the wall, we're coming off with some final momentum in the y and some final momentum in the x. Now, it's important that they told us that there's the same angle and the same speed that it comes off with. And so what that means is that there was no speed that was lost, so pretty much no energy loss or momentum loss here. And the other thing that means is, if we look at the symmetry here, that the y component never really changed. So our initial component in the y is equal to the final component in the y for our momentum, which means the only change, the only impulse is really coming from the x. And so we had to go from a positive pix to a negative pfx. And these two are pretty much the same in magnitude. And so your impulse is basically going to be double that in the opposite direction. The change is going to be double that. So let's say you went, let's say pix is 10 and pfx is negative 10. Well, how did you get from positive 10 to negative 10? Well, you must have gone backwards negative 20. And so our change was, negative double. And so this arrow represents our change of momentum or our impulse. So that's kind of how we're going to think about the problem and how we're going to solve it. So we're going to find the x and y components of our initial and final momentum. And then we're going to take our final momentum and subtract it from the initial momentum to find the change in momentum, which is the impulse. We're also going to assume that the ball's speed is much, much less than the speed of light, which means the gamma is approximately equal to 1, so you have no relativistic effects. And then we can also ignore the effects of gravity during the impact here. And so to solve the problem, what we're going to do is look at the initial momentum right before. And so initially it's coming in with mv cosine theta for x and mv sine theta for our y and 0 for the z. And then just after, it's going to be negative mv cosine theta and a positive mv sine theta. And so notice how the y did not change and the x pretty much just reversed. And so when we do that math, final minus initial, we end up with a negative mv cosine theta minus mv cosine theta is going to be negative 2 mv cosine theta. And that's kind of what we were talking about with it's going to be doubled in the negative direction. The change was double negative. And then we also have this idea of mv sine theta minus mv sine theta is 0, so there was no change in the y, and there's obviously no change in the z. And so that's how we do this first problem. We basically are looking at finding the impulse given to this ball by the wall. And it just so happened in this problem that it's only giving it in the x, not the y. All right, so let's look at another problem. So in this problem, we are finally going to use the idea of the position and momentum update. And so we have a ball of mass 2 kilograms, and we have that it's moving with some initial velocity 1.5 meters per second. And so we have some motion in the z dimension, which we might not be used to. But if we look at our coordinate system here, we're basically understanding that the x and z axis makes up this plane. The xz plane represents the grass or the field, and then the y-axis represents going up into the air or down into the ground. And that is our coordinate system for this problem. And we have a kick that we are going to deliver to this ball that's moving, and the change of momentum from that kick is going to be 4 Newton seconds in the negative x direction. And then after that kick, we have a net force on the ball, and it's coming from friction in the air, and that is going to be totaling 2.5 newtons in the opposite direction of whatever the motion ends up being after the kick. And so the hint is that we need to solve this problem by first looking at the effects of the kick, and then after that, taking into account the resistive forces of the grass in the air. And so for part 1, we're going to use a time step of 0.5 seconds, and we're going to have to do it twice because we need to figure out what's going on with the position of the ball after 1 second. And so we'll start by drawing some free body diagrams, and we're probably going to want to draw 2 different pictures. This first picture is showing the XZ plane here, and so imagine that you're looking down the y-axis at this, and we have some initial motion in the positive z direction, some initial momentum, and we're delivering an impulse, a force over a certain amount of time in the negative x direction. And so after the kick, it's going to make sense that it's going to deviate its path somewhere in the negative x and positive z, which it is. And then this momentum after the kick can be used as the starting point for the problem after we figure that out, because then we're going to take into account the drag force, which is in the 180, complete opposite direction of the motion. It's resisting whatever the motion is. And this will be the diagram that we're considering after the kick. Now we want to look at the principles and concepts that we might use to solve this problem. As I said before, we're going to try to use the momentum principle, the idea of updating your momentum and updating your position as an iterative process with a time step of 0.5 seconds. And so some of the assumptions that we might make, we're going to assume that the ground is flat, and we're going to assume that that is the XZ plane. And we are going to assume that in the y-axis we don't really have too much stuff going on that's interesting. We have normal force up and gravity down, which are canceling each other out. We're also going to assume that time is going to start immediately after the kick, and at that exact instant the ball is at the origin, so the position 0, 0, 0 is going to be right after the kick. We're also going to assume that the ball's speed is much, much less than the speed of light, so gamma is approximately equal to 1. We don't have to consider relativistic effects, and now we're going to solve the problem. So we're going to do this in 3 steps. The first step is we're going to figure out what the kick does. The second step, we're going to then look at what's going on from 0 seconds to 0.5 seconds, and then we will look at what's going on from 0.5 seconds to 1 second. All right? So let's start by looking at what's happening before to after the kick. We're going to start with this momentum update. And so we have this equation that you saw before. Your final momentum equals your initial momentum plus your net force times your time. If you divide everything by mass, then you end up with this equation here. And this is nice because we have our final velocity that we can get, which is equal to your initial velocity, which they gave us, so 0, 0, 1.5. And we're going to add 1 over the mass, so 1 over 2 kilograms. And then this next part, we can combine the net force and the delta t here to basically be your change in momentum. And we know that that's impulse. We know what that is. And we know that it's going to be 4 Newton seconds in the negative x direction. And so this part combined is your impulse, which we plug in to be negative 4, 0, 0. And when we do that math, we end up with the final velocity, which is negative 2, 0, 1.5. Once we have that final velocity, we can just multiply it by the mass to get our final momentum. And so we just multiply it by 2. Now we have our final momentum, which is amazing. We just want to know what direction that's in. And so if we look at what the magnitude is of that vector, we could use the Pythagorean theorem. And we can say, that the magnitude, the length of that vector is 5. And what we can then do is figure out what our unit vector is, because we would love to have a direction for our final momentum. And so the unit vector that represents the direction of the final momentum here we know that it's going to be some negative x and positive z, but specifically what we need to do is take negative 4 and 3, and we need to divide it by 5. So we're going to divide by the magnitude. So negative 4 divided by 5 is going to be negative 0.8, and we have 0 divided by 5 is 0. We got 3 divided by 5 is 0.6. All right, so now we have our unit vector as well, describing the direction after the kick. So step 2, what we're going to do now is look at what's happening due to the force. So far we haven't really considered the drag force, and so now our time is pretty much starting after the kick, and we're at a position of 0, 0, 0 for our initial position, and we have this drag force that's acting with a 2.5 newtons in magnitude. What we're going to do is take that 2.5 newtons and we're going to multiply it by the unit vector, but it's going to be the opposite. And so notice how we have in the positive z, negative x, we have the unit vector for our momentum, but it's going to be the opposite. And so negative 0.8 becomes 0.8, 0.6 becomes negative 0.6, and that's the unit vector for our drag force. And so we need to multiply that by our 2.5 newtons. And so when I do that, I end up with the net force vector, including that direction. So we have some sort of a positive x component to the right, and we have some sort of a negative z component to our drag force. Okay, so now that we have that, we know that we can do our momentum update, and we have this formula again, and we are going to use our 0.5 seconds for our time, and so we can plug in. We have negative 4, 0, 3, which remember that is coming from our final momentum from the last step. So the final momentum for the last step is going to be equal to the initial momentum for this step. All right, and so that's basically our initial momentum that we're starting with, but then we have this drag force that's going to be slowing us down. And so we have this force here, 2, 0, 1.5 negative, multiplied by our 0.5 seconds. And then we get our final momentum after 0.5 seconds. And notice how we have numbers that are less than what we had before. And so instead of negative 4, we have negative 3, and instead of 3, we have 2.25. And so we are slowing down. We have drag force, and after 0.5 seconds of that drag force, we definitely slowed down in terms of our momentum. All right. So this is a summary of what we have so far. We have the final momentum right after the kick. We have the net force right after the kick, and we know that we are starting at a position 0, 0, 0, and then after 0.5 seconds, we just found what that momentum is. And what we want to do now is figure out what that new position is, because clearly it's not 0, 0, 0 anymore. And so we're going to plug in this final momentum that we just found after 0.5 seconds into the position update. So you should recognize this formula from earlier. Instead of writing the average velocity, you should recognize that we can write it as your final momentum plus your initial momentum over 2m, and that's an equation that we saw earlier. And so when we plug into that, we have 0, 0, 0 for our initial position, and we're plugging in our final momentum, and our final momentum in this case is the one after 0.5 seconds, and your initial momentum in this case is the one at the beginning, which is that negative 4, 0, 3. And so we add those together and we divide by 2 times the mass, and then we multiply by our time step, which is 0.5 seconds, and we end up with our final position after 0.5 seconds of negative 0.88, 0, 0.66 meters. Now notice how that is a negative x component and a positive z, which makes sense because we know we're moving in the negative x, positive z direction, and so it makes sense that our position is somewhere in there, just as a mental check. So here's the final position that we just solved for after 0.5 seconds. What we want to do now is apply this process again because it's an iterative process. We're going to use another time step, and we have the same force that's acting, and so it's going to be slowing down a little bit more. It's going to be moving a little bit more. So what is going on? with the momentum. And so how much is it slowing down? Well, let's find out. So we have our final momentum is equal to our initial momentum. In this case, our initial momentum is whatever it was after 0.5 seconds. And we're trying to find what it is after 1 second. And we're going to add this force that we have that we found in the beginning. We still have that force acting for another 0.5 seconds, and we end up with a momentum after 1 second of -2, 1, 1.5. And so what we do is we'll plug that into our final momentum here, and then for our initial momentum we'll use whatever it was after 0.5 seconds. So right there, we'll plug it in over 2m times that time, and then we also are going to use our initial position as whatever it was after 0.5 seconds. So we got that -0.88, 0, 0.66 for our initial position at 0.5 seconds. And so now we're going to find out what it's going to be after 1 second. And so when you do that math, you end up with your -1.51, 0, 1.13. And so that is your position after 1 second. So that pretty much solves the problem there. But as you can see, you can continue doing this process. If you wanted to figure out what it would be at 1.5 seconds, you would just find the final momentum again, starting with whatever you had after 1 second and ending with whatever you have at 1.5 seconds. And so you find that final momentum at 1.5 seconds, and then you plug that into your position update, and then you can figure out what your final position would be at 1.5 seconds. And so you just continue to step your way along, and you're updating the position and you're updating the momentum, and that's how this stuff works. All right, so we'll move on to the second part of this problem. So the second part of this problem is basically just dealing with the same stuff but using coding. And so we can use VPython, and we can basically plug in our information here, and it gives us these lines of code numbered 1 through 20. And what we want to do here for part A is we want to comment each line of code except for certain lines like the print function lines. And what we want to do is just explain what that line of code does. And so if we look at these lines of code here, we can see that this first line that we care about just sets the mass equal to 2. So you're just kind of defining your variables. The second line of code sets your initial position vector at the origin. Your next line of code here is going to set the velocity before the kick, which we had in the problem. Then you have the idea that we need to calculate your momentum before the kick, so your momentum is just mass times velocity, right? And then we have our impulse that we're giving it, so we have that -4 impulse in the x, 0, 0. So you're setting your impulse in that line of code. The next one is you're calculating the momentum after the kick, so your momentum after the kick is going to be whatever it was before plus whatever change there was. You also have to calculate the velocity after the kick. The velocity is the momentum divided by the mass. And we also want to define our unit vector, so we use a hat for that, so v hat, and that's going to calculate the unit vector in the direction of the velocity. And we also are setting dt, so our time step is 0.5, and your initial time that we're starting at is 0. And then we're going to start this loop here, and we're going to calculate the new momentum. So you have your momentum update here, and then we calculate our new velocity, we calculate our new position, so you have that position update, and then we want to have this in increments, and so we got to increment the time by the time step, and so that's how you do that. And so that's part A, commenting on this code and what it's doing. And the nice thing about this is that, you know, once you run the program, it'll basically solve everything for you, and it'll give you pretty much all the answers that you want, which is awesome. And so the next problem here, if you read the output of the program, what would you need to focus on to figure out the time and position when the ball stops. Well, you would want to find the time when the velocity is 0, because that's when you know it stops. We know it's eventually going to stop because it has the resistive force. And so, common sense tells us that too. If you kick a ball on a field, it'll eventually stop. And so we would want to find where that velocity becomes 0 or reverses direction, and then we would look at the position at that time step. And so that's what we would do. All right, so the last part here. So in this last part, we basically want to think about what would happen if the opposing force was proportional to the speed. And so instead of being 2.5 newtons in the opposite direction of the motion the whole time, what if it changed as a function of speed? So the faster you go, the more resistance you have. And this is a little bit more realistic, because if you think about, let's say, traveling on the highway at 60 miles per hour and sticking your hand out of the window, you're going to be feeling a lot more force resisting your motion compared to if you were just traveling like 5 miles per hour. Another way of thinking about it is if you jump out of an airplane and you start accelerating towards the ground, you're not going to accelerate to some infinite velocity. Eventually, the resistance from the air is going to equal the gravity. And so at that point, you're at your terminal velocity. So the acceleration stops at that point. And so in this situation, we're only considering the resistive force on the ball pretty much. And so your net force is this negative B, B just representing the strength. So it's a constant, the strength of the resistance. And so it's proportional to velocity. And so let's say that B is 0.8. And so they want to know, how would you change the code to simulate this situation? And so here's the original code that we have. And so what we would do is just modify it a little bit. Notice how a lot of it is the same, but we do have some key differences. So we do want to make sure that we define what B is. So B is 0.8 here. And then instead of having our net force like we did before of the negative 2.5 times the v hat, the unit vector, we want to make sure to define it as the formula that they gave us. So negative 1 bv. And so that's the kind of the key difference in the code that you want to make sure that you understand. And so hopefully this idea of a momentum update and position update makes sense to you. Working with forces, working with some of those kinematic equations, and we will see you in the next one.